Welcome to section 7.6, Logistic Functions. At the end of this video, we should be able to answer these questions. What is a logistic function? What are the key characteristics of a logistic graph? What is the general equation for a logistic function? What are some real-world examples of logistic functions? How do we solve for a particular logistic function given data or a graph? Well, let's talk about what a logistic function is. A logistic function is a graph that looks like this, which has a lower bound and an upper bound. We start low, we have this rapid increase in the values of y, similar to an exponential graph, and then halfway through our journey from the lower bound to the upper bound, our graph starts to slow down and changes from a concave up graph to concave down, eventually leveling off at this upper bound, which we'll call C for the purposes of discussion. So halfway through this graph, we have this point of inflection where our concavity changes from concave up to concave down. Now let's talk about what type of equation would generate this type of graph. Here's the general equation for logistic functions. It's in two forms, one with a base of e being used and one with a base b. You'll see that our f of x has this value on top, c, over 1 plus ae to the negative bx, or c over 1 plus ab to the negative x, where a, b, and c are constants. So these are the three unknowns we would have to solve for in given a set of logistic data. The domain is all real numbers. Let's take a moment and see why this equation generates this graph. Let's think about what happens as x gets larger and larger to this expression. Now as x gets larger and larger, we're multiplying it times a negative number, and any number raised to a large negative number becomes very, very small. In fact, so small we could almost consider it to be 0. So we end up with a times a number very close to 0, so 1 plus a very small number. C over that number would just end up being basically c. Now if x were a negative number, then we'd be multiplying a negative times a negative here, and e to a very large positive number, when x is a large negative number, becomes a large number. So I'm adding 1 to a very large number. So c gets divided by a very large number, eventually becoming very, very close to 0. So if we go back to our graph, you can see that as x gets more and more negative, we're dividing by larger and larger numbers and eventually getting very, very close to 0. And as x gets more and more positive, we get closer to having c divided by 1. So our graph levels off at y equals c. Populations are good examples of how this type of graph plays into the real world. Most populations start out with a very few members of the society, and as they take advantage of the resources around them, the population grows and grows rapidly in an exponential manner. But as the population grows and demands more and more resources, the environment can't supply the necessary resources to sustain that growth, so the growth slows down until we reach this equilibrium where our population and our resources match exactly.